Hi everyone, this is Mrs. GA, and today we are going to learn how to graph logarithmic functions. Before we start graphing, I have a quick warm-up for you guys, so go ahead and pause the video and give these 4 a try. We'll check your answers in just a few moments. Alright, so when you're evaluating logarithms, the important thing to remember is that logarithms define exponents. So we're essentially saying, if my base is 4, what must the exponent be to get 16 as my result? So log base 4 of 16 must be 2. Log base 2 of 1/2 must be -1. So remember to cause that reciprocal action, it means your exponent is negative. 3 to what power is 3? 1. And then log base 7 of 1 must be 0. So remember, any number, any base to the power of 0 equals 1. Alright, so to start our discussion on the graphs of logarithmic functions, we're going to look at what the general shape of our logarithmic functions are. So just a quick reminder, if you have the exponential expression x equals b to the power of y, we can rewrite it like this: y equals log base b of x. So that logarithmic function is the inverse of our exponential function. And also remember, by definition, our b value, that base number, must be positive, but it cannot be 1. So any other positive number. So there are 2 general shapes that logarithmic functions make, and that depends on the size of your base number. So if your base is greater than 1, like you see here, you have this increasing graph that kind of flattens out the farther you head towards positive infinity. And if your b value is between 0 and 1, still positive, right, you have this decreasing graph like this. So you see it's just a reflection over that x-axis. One thing hopefully you notice about both of these graphs is they both share the same 2 points. So all of your parent functions will go through the points 1, 0 and b, 1. Okay, and the reason for that, let me slide to the side a little bit. Imagine that you have log base anything b of 1, right? We know that the only way to achieve that, any base to the power of 0 equals 1. So again, that's why we have this point 1, 0. Your x value is 1, your y value is 0. And then for this point right here, so let's say our x value is b. So let's say we have log base b of b. Well, you have b to what power equals b? Well, b to the first power equals b. So again, these 2 points will be on all of your parent functions. So those are 2 points, really great points to start with. Another thing you'll notice that both of these graphs have a vertical asymptote at x equals 0. That's because we do have a restricted domain. So let's add those in for asymptotes. So x equals 0 is for both of them. Vertical line on the y-axis. Okay, of course that could shift left or right, but that will be true for all of our parent functions. So now let's see if we can define the domain and range. And I'll use interval notation here. So for the domain, you can see that it is restricted. It's all the x values. So it's actually going to be everything greater than 0, but not equal to 0 because we never actually touched the asymptote. So we'll do 0 to positive infinity. And you can see that for our range, it's going to go down forever and up forever, so our range is all real numbers. So negative infinity to positive infinity. We have the same domain for our decreasing graph. So our domain is 0 to positive infinity, and our range is all real numbers. Okay, now let's talk about end behavior. So we're going to describe what's happening on the left and right side. So let's start on the right. So this is going to be as x approaches positive infinity. So we can say as x approaches positive infinity, we can see that our graph is going to head towards positive infinity. It's going up very slowly, but it's still going up. So f of x approaches positive infinity. Now here's something that's a little bit different. Going to the left, our end behavior is actually as x approaches our asymptote. So here we say as x approaches 0, f of x approaches negative infinity. You can see as our graph approaches 0, our graph is heading down. Okay, so This time our end behavior going to the right is as x approaches infinity, and going to the left it's as x approaches 0. So it's going to be very similar for our decreasing graph, but the f of x is flipped. So here, as x approaches positive infinity, which is going to the right, you can see that our graph goes down forever. So f of x approaches negative infinity. And then here, as x approaches your asymptote at 0, our graph is going up forever. So f of x approaches positive infinity. Here, our x-intercepts are the same. It's going to be 1, 0 for both, and that will be true for all of our parent functions. And our y-intercept, well, since in this case our y-axis is an asymptote, we would actually say does not exist. Now, of course, that could change if our graph is shifted to the left, but for our parent functions, again, these will all be true. So now that we know what the general shape of our graphs are, and we even have some nice key points we can start with, we can then graph other versions using what we know about transformations. All right, let's try to graph these two logarithmic functions together. So these would both be parent functions. This would be the parent function for a base 5, and this would be a parent function for a base 1/4. So we're going to fill out a t-chart here. So when you're picking your x values for logarithmic functions, it's really important that you pick very strategic numbers. So notice that I have 1/5, 1, 5, and 25. So I essentially always pick the reciprocal of the base. 1 is always a good one, 5, and 25. So here we're just going to be evaluating our logarithm to find those points. So for that first one, if x is 1/5, that's saying log base 5 of 1/5. So we're evaluating. So we're saying essentially 5 to what power is 1/5? That'd be negative 1. The next one is log base 5 of 1. So if x equals 1, so 5 to what power equals 1 must be 0. Remember, all of our parent functions will go through that point 1, 0. And then we have log base 5 of 5. 5 to what power is 5? 1. So that's that b1 that all parent functions will go through. And then we have log base 5 of 25. So 5 to what power is 25? 5 squared. So again, it's important that you're picking strategic x values that work well with your base. So let's plot those points and see what it looks like. So for 1/5 negative 1, you can kind of just estimate where that would be right here. Then we have 1, 0, and 5, 1, and the next point goes way off our graph, so don't worry about it. So we get a graph that looks like this, one of those increasing ones. And we know that we should have that vertical asymptote right here. So we can sketch that in with a dotted line. So our domain, again, is from 0 to positive infinity. Our range is all real numbers, negative infinity to infinity. Our end behavior would be as x approaches positive infinity. That means moving to the right. F of x approaches positive infinity. Our graph goes up. And then going to the other side, our graph is approaching 0. So we say as x approaches 0, f of x approaches negative infinity because our graph is going down. For the x-intercept, we have that at 1, 0. Y-intercept does not exist because there is an asymptote, and that asymptote is a vertical line, so x equals 0. All right, let's try one more. So here you'll notice that I left out the x value, so let's pick some strategic ones. So with the base, it's always good to do the reciprocal, so we'll do 4. We should always do 1, and then we should match the base 1/4, and we can either pick 1/16 or we could pick 16. Either way, we're going to get the same general shape. So let's evaluate. So here, log base 1/4 of 4 when x is 4. So 1/4 to what power is 4? Must be negative 1. We know it's negative because negative exponents cause that reciprocal. So we have negative 1. And here, log base 1/4 of 1, 1/4 to the power of 0 is 1. So there's that point that all of our parent functions go through. Here, 1/4 to what power is 1/4? It's 1. And last, log base 1/4 of 1/16. Here, 1/4 to what power is 1/16? Well, it's going to be squared. So 2. So now we can plot our points. So we have 4, -1, 1, 0. And then the next two we'll kind of just have to estimate. So like this, and then like this. So from here we know that we should also have that vertical asymptote at x equals 0. So let's do our domain and range again. The domain should be the same as example A, and so should the range. And behavior is similar, so as x approaches positive infinity, moving to the right, you can see that our graph is going down. So f of x approaches negative infinity, and then as x approaches 0, which is what's happening on the left, our graph is going up. So f of x approaches positive infinity, our x-intercept is at 1, 0, our y-intercept does not exist, and our asymptote is that vertical line, x equals 0. All right, so I have a few here for you to try on your own. The key here, again, is going to be picking the appropriate x values, then finding those y values, graph, and then name the characteristics. So go ahead and pause the video and give these a try. All right, go ahead and check your work here. So you can see here, look at the x values I chose to help me get easier y values. So you'll notice that all the characteristics are all the same for the increasing one. So when your b value is bigger than 1, then all of your characteristics are the same for when your b value is between 0 and 1. So again, check the x and y values here in your graphs. And then down here, again, problem it should be C here, is very similar to problem A. All of the characteristics are the same, just your values are a little different. And then here your last example is very similar to the second example. So just go ahead and check. I know this was a little bit repetitive, but hopefully by the end of this, you really will remember what the end behaviors are, the domain, range, asymptotes, and x-intercepts. All right, so to end off this lesson, we are going to do a little extra practice of evaluating our logarithmic functions just to review it. So here we have the function f of x equals log base 5 of x. So first we're asked to find f of 25. So that means our x value is 25. So let's write that in. Log base 5 of 25. So again, when we're evaluating, we're essentially trying to figure out what the exponent is. If it helps, you can rewrite it like this. 5 to what power would equal 25? So this logarithm is equal to 2 because 5 squared is 25. Remember, logarithms define exponents. So here we have f of 1 over 625. So that means that our our x value is 1 over 625. So again, you think of this as 5 to what power is 1 over 625. Well, here I know that 5 to the power of 4 is 625, so it's going to be 4, but notice that it's 1 over 625, so the way to create that reciprocal is by making your exponent negative. And last but not least, f of the cube root of 625, so log base 5 of the cube root of 625. So again here, we're saying 5 to what power is the cube root of 625. Since we have that radical, I know that our exponent is going to be a fraction. So on the inside, so our x value, we know that 5 to the 4th power is 625. So that's going to be the numerator, but then it's a cube root here, so that becomes our denominator. So you bring it to the power of 4, and then you cube root it. So our answer is 4 over 3. All right, so that is all for today's lesson. Thank you so much for watching.